In this video, I'm going to talk about Faraday's law. We saw in the previous video what magnetic flux was, and we learned previously that when we change the magnetic flux through a loop, there will be a current induced. So Faraday's law is going to put this in writing for us. Here's Faraday's law. It says that the magnitude of the induced EMF is the rate of change of the magnetic flux through the loop. So you saw in a previous video, if you didn't see it, I have the link here for you again. But you saw that when the person put the magnet through the loop, that a current was induced, and if he put it through the loop very quickly, there was more current induced than if he put it through the loop slowly. So this means that the rate at which the flux was changing, the rate at which he was changing that magnetic field through the loop, affected how much current was induced. So that's what this rate of change of magnetic flux here, that's what this is saying. How fast you change the flux is going to affect how much current induced. Now Faraday's law is giving us how much EMF is induced. Well, we learned previously that EMF is basically your voltage source, right? What is providing that voltage or that energy? And you can use Ohm's law, which says that the current is the voltage or the EMF over R, to see the relationship here. If there's a current induced in a loop when the flux changes, then that means that there has to be some kind of EMF that is causing that current. So Faraday's law tells us how much EMF is induced, but then we can divide it by the resistance of that loop to find exactly how much current is induced as well. What I've done is I've rewritten Faraday's law to make it a little bit easier to use. So what it says here is that the EMF induced here is equal to the number of loops multiplied by how quickly the flux is changing. I'm taking an absolute value because I just want to use Faraday's law to tell us the magnitude of the EMF induced, how much EMF is induced. We're going to worry about the direction in the next video, which will be about Lenz's law. For now, we just want to find the amount of EMF. So there are different ways to change the magnetic flux through a loop. Remember that the definition of magnetic flux is BA cosine theta. So one thing we can do is we can change the field through the loop. And problems that will be given will only be changing one parameter at a time. So if we're just changing the field through the loop, then what we can do is look at how quickly we're changing the field, that's what this term is, and we can bring the A outside, because if we're not changing the area, then you don't have to have a delta in front of it since you're not changing it. And since I've removed the cosine theta term, then I'm assuming that the magnetic field is perfectly perpendicular to our loop. We learned previously that if the field is perpendicular to the loop, then the angle is 0 because it's the angle between the normal to the loop and the field, so that cosine term cancels out. Cosine of 0 is 1. And the other thing I've done is I said, well, what if we're just changing the area of the loop? Then we can write Faraday's law like this: the EMF induced equals N times the magnetic field, which is not changing, and then multiply it by how fast the area is changing. Let's do an example of Faraday's law. We have a coil which is 6 centimeters in diameter is placed in a field. Does that mean that there's a current induced? Well, only if there's a change in flux, and in this case the field is changing. So if the field is changing, then that will change the flux. Let's take a look, write down our givens. So we're given the diameter of the loop, 6 centimeters, 0.06 meters. Let's find the radius, which is half of that, so 0.03 meters. And while we're at it, let's go ahead and find the area of that circular loop, pi r squared, which will give us 0.0028 meters squared. And then the field is 0.50 Teslas, but it drops to 0 Teslas in 0.002 seconds. So the change in the field, final minus initial, is 0 Teslas minus 0.5, or negative 0.5 Teslas. And then how long it takes to change the field is 0.002 seconds. So let's go ahead and write Faraday's law. Since we're only changing the field, we can write it as follows: the number of loops times A, the area times how fast that field is changing. How many loops do we have? It just says A circular coil, so N is equal to 1. So all we have to do is plug in these numbers. 1 times 0.0028 times, and we're taking the absolute value here, we don't care about the sign, so 0.5 divided by 0.002. Again, you can put the negative here, but we're taking the absolute value, so the negative doesn't matter. We're multiplying all of these things together, and we're going to get 0.71 volts. So this is how much EMF is induced in the loop, which in turn will produce a current in the loop. We'll explore the direction of that current in the following video, where we're going to discuss Lenz's law.